be here. To motivate some of the work that I'm going to be presenting today, I'd first like to give a motivation, give a fairly broad picture of some of the machine learning that exists today. So I think some of the biggest success stories of machine learning have been in supervised learning. Things like object detection, machine translation, speech recognition, to name a few. And these systems work really well, they're really useful. By using deep networks, they can handle raw sensory observations. And pretty importantly, they can scale to the diversity of the real world. So an individual user can upload their own images, their own speech, and these systems can handle them reasonably well. But from the perspective of building artificial intelligence, I think these systems are a bit dissatisfying. And that's because these systems require tons and tons of detailed human supervision in the form of input-output pairs. And further, these systems learn completely passively. So in order to improve themselves, they rely heavily on humans to provide them input-output pairs, to provide them labeled data. And as a result, I don't think they have any hope of exhibiting the kinds of intelligence that humans have. So how can we move away from such strong supervision? Well, one thing we can do is have agents that interact and learn through interactions with the world. We've seen exciting advances in this direction too. So we've seen agents that can learn to play Atari from raw pixels and defeat grand champions in Go, which is quite exciting. These systems, by using deep networks, they can handle raw sensory observations like pixels. And by learning through interaction, they can learn through more high-level word feedback, such as reward functions that a human might provide. But one thing you might notice here is all of these domains are domains that can be perfectly simulated. And the reason for that is that algorithms underlying these advances require massive amounts of experience in the environment. And further, you might notice the diversity of the environments seen on the right is drastically less than the diversity that the systems on the left can handle. And as a result, these systems exhibit a much narrower notion of generalization. So looking at this work, I think to me there's two questions that arise very naturally. First, can we build reinforcement learning systems that are efficient enough to run in the real world rather than in simulated domains? And second, can we develop systems that can learn many different tasks in many different environments without a lot of supervision? Okay, so first I'd like to talk about the first question, very briefly actually. So I did some work on the first question of very efficient reinforcement learning at the very beginning of my PhD, and I'd like to summarize that work on this slide. And that work was considering the question, can we learn sensory motor skills from raw pixels on a real robot? And to approach this question, we need efficiency in our reinforcement learning algorithms. And so to approach it, we combined insights from deep learning as well as from optimal control in order to develop a reinforcement learning algorithm that is significantly more efficient than the other algorithms. So here you see, this is Brett the robot. Brett's trying to learn a policy that maps from raw image pixels taken from the robot's camera to torques applied at the robot's joints. In this particular case, the robot is trying to learn to insert this red block into the matching hole on the shape sorting cube. At the beginning of learning, the robot is executing fairly random motions. And as you can see through experience, the robot can relatively quickly learn a policy that can successfully insert the block into the shape sorting cube. And here's the final policy that it learns. So we can see that it can learn in, for example, when a human is holding the block.
How many trials does it have to do?
Yeah, so in this case, it took around 2 to 3 hours to learn. That includes learning the vision part of the network. And actually, a lot of that was computation time with the GPUs that we had about 4 years ago. Okay, and beyond inserting a block into shape sorting cube, the robot could also learn how to insert the claw of a toy hammer underneath the nail, screw a cap onto a bottle, like this, and also use a spatula to lift an object and lift it into a bowl. This last task is actually quite challenging because the robot needs to fairly aggressively maneuver the spatula underneath the object in order to successfully lift it.
Do you have separate policies for separate tasks, or is it just?
Yeah, in this case, it's separate policies for separate tasks. Beyond the work that we did at Berkeley, there's a number of labs at KTH, at Google, at USC that built upon the work and put the work on their own robots. Okay, so this is really nice. This means that we can learn complex behavior from raw pixels, starting from scratch, and we can do it on a real robot. So what's stopping us from putting these robots out in the world and having them help humans and help society? Well, the issue, as pointed out, is that these robots and all of the machine learning systems that I showed on the previous slide are what I would call specialists. which is that they learn a single task in a single environment starting from scratch, disregarding a greater understanding for how the world works and how objects work. And as a result, they can't generalize. That robot learned how to use that spatula and lift that object. And if you give it a different spatula or a different object, it would have to learn again starting from scratch. Humans, on the other hand, learn very differently. So humans learn by rolling around on the floor, playing with objects. And critically, humans learn many, many simple tasks, like picking up objects, like crawling, before trying to learn more complex tasks like using a spatula. Humans are what I would call generalists, in the sense that humans learn many different tasks. They build upon their previous experience in order to learn new things, and they exhibit common sense. And I hypothesize that if you can build machine learning systems that are generalists, they'll be much more broadly useful and broadly applicable than the machine learning systems that we have today, because they'll be able to use their understanding of the world in order to understand what humans want and understand how to do things in new situations. Okay, so how do we get there? To build machine learning systems that exhibit the intelligence of humans, I think they need to learn a lot more like humans. So I think they need to be able to handle raw sensory observations, be able to learn in diverse environments, be able to build upon previous experience to quickly acquire new skills, and also to be able to learn with minimal human supervision. So how do supervised learning systems compare? Supervised learning systems can handle raw sensory observations and diverse data. Although, while these algorithms are quite general, so you can apply supervised learning to many different types of problems, they learn each problem and each skill from scratch. And they have to start from scratch. So you can't build upon something else that you've learned previously in order to quickly acquire a new skill with less data. And further, as I mentioned before, supervised learning systems can't learn from minimally supervised data. Okay, and reinforcement learning systems, they can handle raw sensory observations. They haven't yet been demonstrated in diverse environments, typical of those seen in supervised learning systems. They can't acquire new skills with few examples. Again, the algorithms themselves are quite general, but they learn everything from scratch. And they require less supervision than the deep supervised learning systems, but in practice, most reinforcement learning systems often either involve very, very large amounts of data or fairly shaped reward functions or fairly detailed supervision still. So my ultimate goal is to bridge the gap between learning systems that we have today and humans. And likewise for probably many of you. And in this talk, I'd like to pose two questions that I think will bring us closer to bridging that gap. The first question is, can we enable machine learning systems to acquire new capabilities with small amounts of data by building upon their previous experience? And second, can they learn to do so without any human supervision, or at least with very minimal human supervision? Okay, so kind of with these questions in mind, here's an outline of what we'll be talking about today. So first, we're going to be talking about, can we have algorithms that build upon their previous experience and learn how to learn new concepts and new capabilities with small amounts of data? Second, can we meta-learn these representations without any human supervision, with unlabeled data and unlabeled experience? And finally, I'd like to talk about how we can do this on a real robot and actually adapt online to changing environments. And then I'll conclude by discussing future work. Okay, so first let's talk about learning how to learn new concepts from small amounts of data. And to do this, we're going to build upon the notion of meta-learning and few-shot learning. And first, I'd like to introduce kind of what is the problem statement underlying meta-learning in order to try to get a handle for the types of algorithms that we might develop. So first, let's look at supervised learning. So in supervised learning, our goal is to take in inputs x and produce outputs y. So learn some function that goes from x to y. And the way that we learn this is through data in the form of input-output pairs. Now, in meta-learning, our goal is to be able to learn from data and make predictions about new data points. So our goal is to be able to learn something that takes as input a data set. This data set will consist of k input-output pairs for the k-shot learning case. This is what we want to be able to learn from. And additionally, we want to be able to make predictions about new data points based on what we learned from this data set. So additionally, one of our inputs is going to be a new data point that we want to be able to make predictions about. And our goal is to produce the label for that input based on what we learned using the data set. Okay, so how do we go about learning this learning procedure, essentially?
So I'm confused. What's really the difference between the top and the bottom, other than, I guess, k is expected to be small?
So in the top case, your goal is to learn some function, like from image to label, for example. Whereas in the bottom case, your goal is to learn from a data set of data points and make new predictions based on those data points. You can pose this as a supervised learning problem where you just like combine X and your training data set and directly map from the training data set to and the new data point to your test output. But there's also a bit more structure in this problem that you can use in order to more effectively solve this problem. Like you can use the fact that this is a data set and we want to be able to learn from this data set.
So formally, is one strictly harder than the other, or are they? I'm sorry, I'm still confused about how they. You were kind of explaining the first one with an analogy, but are these formally different? Is one strictly harder, a harder sample complexity?
I mean, there isn't that much I guess we haven't really gotten to the point of studying like the kind of the complexity and the difficulty of these problems, like theoretically speaking. I would say in some ways I think the meta learning problem well, I guess it seems like there's more structure to the meta learning problem than to the supervised learning problem. And with that structure, you can, I guess, design algorithms. I guess there's things that you can do that are better than just like throwing a big neural network that takes in the data points and produces the outputs. And I'll talk a bit about that later. Okay, so given this problem statement, our goal is to learn a mapping from training data set and test input to test output. And the way that we learn this is through a data set of data sets, where each data set consists of typically more than k input-output pairs. So you can sample k to be used in your training data set, and at least one to be used to measure generalization, and actually drive learning performance from your meta learning algorithm. Okay, so let's look at, now that we've defined the problem statement, let's look at a few different examples of how we might use this, a few different examples of what this problem statement looks like. Okay, so first let's look at the few-shot learning example, the kind of the few-shot classification example, which is a pretty common example in the meta learning literature. So the goal of this is the following. So say you're given one example of 5 different classes. This is going to be your training data. You want to be able to classify new examples as being among those 5 classes. You need to figure out which of these 5 classes these images corresponds to. Now, how might you go about trying to solve this few-shot learning problem? In particular, what if you had image data from other image classes? How could you use that data to effectively solve this problem? Well, what you could do is you could structure the data from other image classes just like how you're going to be presented at test time. So you can structure it, you can sample 5 classes and put it into a training data set and a test input and test data points. And you can do this for many different sets of classes. And then these will be your training classes, so you'll meta learn across these training classes so that when you see new held out classes, you're effectively able to solve the few-shot learning problem. Okay. So this is one example. Let's look at a couple others. So one example is the ability to create a goal classifier or a success detector. And in robotics, and if you want to be able to generally convey goals and different types of tasks to an agent, this is actually quite important. An example of this is, say we want to be able to tell a robot how to set a table. In this case, the goal is to put the knife to the right of the bowl. You want to be able to just give it 2 examples of success in this case, and have it be able to learn a classifier from just those 2 examples for new images. And again, if you want to think about how we try to solve this few-shot learning problem, we can say that we have data from a number of other tasks. For example, putting pencil cases on top of notebooks and other objects and other arrangements, and have it learn across all of these tasks so that when it sees a new task and only a few examples for that task, and it can effectively learn a classifier for it. Okay, and then just quickly one last example, let's look at the imitation learning setting. So in this case, our goal might be able to learn from a video of a human doing a task. So we could view our training data as a video of a human performing the task, and then our goal is to be able to learn a policy from that video that takes in new camera observations from the robot's camera and outputs the action of the robot performing the task. And again, how we might do this is collect videos of humans and teleoperated robot demonstrations and have it learn how to take as input the video of the human doing the task and the new image that the robot sees and produce the corresponding action. Okay. So now that we've seen a few examples, let's actually think about the algorithms and how do you actually go about solving these problems. So many of it comes down to the problem of designing this function f that's going to map from d-trained x task to y task and optimizing that function. And the first thing worth mentioning is that there's a lot of work on trying to design and optimize these functions, from things like using memory to learning optimizers through things like reinforcement learning, as well as metric learning approaches that try to learn a metric space for which these problems can be solved. And I'd like to highlight one particular previous approach that has been, in a sense, the most general, and that's been applied to a number of different meta-learning problems, and I guess has a lot of expressive power in the types of meta-learning, in the types of learning procedures that it can acquire. And that is the idea of just using a recurrent neural network. So as I mentioned before, you could just take a recurrent neural network and have it take as input your training data set and your test input and produce a prediction for that test input. And you can just train this with supervised learning. So this approach is quite nice in that it's quite expressive. It can represent a lot of different potential learning algorithms from this data. And you can train it on a number of different problems. It's fairly generic in that way. But one of the downsides of this approach is that it's a very complex model and it has to perform the complex task of learning from this data. And as a result, even if you can effectively optimize this recurrent neural network, it often requires impractical amounts of data in order to try to learn how to learn from scratch from this data. So if we take a more principled approach, can we improve upon this method? Well, so I guess when thinking about this, we tried to take some inspiration from a very successful method in transfer learning. It's not necessarily meta learning per se, but one of the most successful methods for transferring from previous data sets to new data sets is the idea of fine-tuning. If you pre-train a model on something like ImageNet per se, and then fine-tune it on a modestly sized data set, you can actually do quite well on that new data set. It's a method for transferring all the rich information in ImageNet towards your new problem. And so the way this works is you have some set of pre-trained parameters. This could be something trained on ImageNet. And you run gradient descent, initialize those pre-trained parameters on data for your new task. And typically this works well for fairly modestly sized data sets when you have your new task. But this will only go so far. So if you only have, say, like 5 data points for your new task, you're still going to massively overfit to that data. So can we take in some inspiration from this approach and try to devise some pre-training such that we can actually just run gradient descent with respect to new data sets, even if they're quite small? So this is what we want to be able to do at test time. We just want to run gradient descent, the same procedure as what we would do if we were learning from scratch. Well, what we could do is, what if we explicitly optimize for a set of pre-trained parameters such that when we ran gradient descent with respect to a small amount of data, we effectively generalized to that task and to that data. In particular, what we're going to do is we're going to optimize basically exactly what I said. So we're going to optimize for a set of initial parameters such that one or a few steps of gradient descent with respect to a small amount of training data does well on new data sampled from that task. So essentially what this amounts to doing is training over many different tasks to learn a parameter vector that can transfer effectively when you fine-tune via gradient descent. Okay, so intuitively what this might look like is, say theta is the parameter vector that we're meta-learning, and theta I star is the optimal parameter vector for task I. We can view the meta-learning process as this thick black line, whereas when we're at this point during the meta-learning procedure, we take a gradient step with respect to task 3, we're still quite far from the optimum for task 3. Whereas at the end of meta-learning, if we take a gradient step with respect to task 3, we're quite close. And likewise for a number of other tasks. Yeah?
So I'm guessing from your notation that the algorithm is not sensitive to the ordering of the tasks?
What do you mean by that, I guess?
I mean that the kid, right, first learns to crawl then learns to walk, then learns to play basketball.
Right, yeah.
So there's a, the curriculum is ordered.
Yeah.
I guess I was trying to ask, is your curriculum ordered or not?
Yeah, so in this case, I guess generally the meta learning problem is more like one slice of the lifelong learning problem, where you assume that you have a set of previous tasks, and you're trying to learn those tasks so that the next task you see, you can learn very quickly. And we have started to look at trying to apply these in lifelong learning settings, but we haven't quite gotten there yet. Okay. So we refer to this procedure as model agnostic meta learning in the sense that it's agnostic to the type of model that you use, which is quite nice. It means you can apply it to a wide range of problems. Okay. So now let's think about how this compares to the recurrent neural network that I mentioned. So NAML is essentially just running gradient descent starting from some pre-trained initialization at test time. If we want to think about these two different learning procedures that they learn, we need to think about what learning procedure the recurrent neural network learns. Essentially what it learns is implemented by a forward pass through this recurrent neural network. And then we can ask some questions about this learning procedure in order to kind of think about how these two compare. The first is, does it converge? What does this learning procedure converge to? What do you do if it's not good enough? And we don't really have great, I guess, very satisfying answers to these questions for the recurrent neural network case. I guess you could view it sort of as converging to the last hidden vector of, or hidden state of the recurrent neural network. We have no idea what it converges to. And if it's not good enough, there's nothing we can do to continue to improve, even if we have more data for the test tasks that we're provided with. Whereas in the case of MAML, we're just running gradient descent with respect to our data. So we know that it does converge, and it converges to a local optimum because we're just running gradient descent. And if it's not good enough, what we can do is we can keep on taking gradient descent steps. And even if we have more data, we can keep on integrating that data by running gradient descent. And we found this property to be actually quite nice in a number of different applications, because in many cases you can potentially collect more data if you need to. Yeah?
By this last point, do you mean keep taking gradient steps with respect to this new train set?
So I mean taking gradient descent steps with respect to the data set that you have for your test task. You might only have like k data points for that task. You can keep on taking gradient steps on that, although at some point you will converge. Also, if you have more than k data points, or you realize that you're not good enough after those k data points, then you can keep on collecting data and taking gradient steps with respect to that new data. Yeah.
And during this setup for MAML, how come you only have one gradient step?
So we write that down for notation just because it's easier to write that down. In practice, we typically use between 1 and 5 gradient steps. More than that, we haven't really found to be particularly useful. Yeah.
Can you think of this as the one on the left is trying to learn how to learn, and the one on the right is trying to learn where to start learning from?
Potentially. I guess one thing, so I guess the next slide will maybe get at this a little bit more. And so I can move on to that. There's also one other question that I would like to, yeah.
So are you assuming basically these data sets or tasks are separate?
Yes, so it's very important to assume that the tasks at least share some common structure so that when you learn that structure, you can effectively use that to more quickly learn a new task. And if they don't share any structure at all, if they're just like randomly sampled from some uniform distribution, then there's no structure really you can tie onto, and at the worst case, you'll just be learning from scratch. Okay, so we can revisit your question after the next slide. So one kind of natural question after thinking about using these properties is that, are we getting these nice properties at some cost? In particular, you might wonder, well, the recurrent neural network is clearly extremely expressive, whereas with the structure of gradient descent, maybe that's limiting the expressive power of this meta learning algorithm, and it's only learning potentially where to start, rather than actually learning more about how you actually go about the learning process. And so to think about that, we tried to measure the expressive power of the learning algorithms acquired by these two meta learning methods. To do this, we needed to define some notion of expressive power, so we defined what we call a universal learning procedure approximator. And in particular, what we mean is a universal learning procedure approximator is something that can approximate any function of the training data set and the test input. So essentially, just a generalization of the universal function approximator to the setting where you have data sets and test inputs. It's pretty easy to show that the recurrent neural network satisfies this property, and it can approximate any learning procedure in this sense. But it turns out that you can also show that gradient descent with the learned initialization can also satisfy this property if you have a sufficiently deep function hash. And why this is interesting is it means that we get all the nice properties on the previous slide and the inductive bias of incorporating gradient descent into this process without losing expressive power. So essentially, the mammal function can represent anything that the recurrent neural network can represent. So this might shed some light on your question in terms of the fact that it can represent the types of learning algorithms that the recurrent neural network can represent. Okay. So now let's actually look at how this works, how it performs. And first I'd like to show kind of an illustrative example that I think does a good job of potentially showing what happens. So this is actually a reinforcement learning example. I mean, kind of considering the question, can we learn a representation under which reinforcement learning is very fast? And in this illustrative example, we're just going to consider two tasks. One of the tasks is to run forward, and one of the tasks is to run backward. And the goal of the algorithm is to learn initialization such that after one policy gradient step, you can either run forward or run backward, depending on the reward function that you're given. And first I'll show the policy of the parameters right here. So this is after meta learning, but before you adapt. And this is the policy that it learns. And essentially what it learns is just to run in place. It's essentially like kind of like ready to run in any given direction. And then if we take one gradient step with respect to the task or the reward function of running backwards, we get a policy that can run backward. And if we take a single gradient step with respect to the task of running forward, we likewise get a policy of the and running forward. I'm sorry, this is a bit choppy over Hangouts. So what this shows is that if you have the right representation, reinforcement learning can be incredibly fast, at least for these two tasks. Okay, but of course this is quite a toy example. We also looked at a more complex meta-learning benchmark, which is the mini ImageNet few-shot classification benchmark. And we found that at the time it was able to outperform some of the state-of-the-art methods, matching networks, and its LSTM optimizer. The blue is essentially representative of the LSTM that I showed previously. And beyond that, the results actually kept on getting better. So there are people that were building upon the work. We originally were getting 63% accuracy on this benchmark. Lee et al. Built upon the work in 2017 and was able to get 64%. And then someone actually ran architecture search on the mammal algorithm, was able to get significantly better performance when you actually tune the architecture in a way that is good for this task. Whereas in the previous results, we were just using a base architecture to make all the results comparable. Okay, and beyond the mini ImageNet benchmark, there's a lot of other people that have built upon the work. Here's a selection of these. And one thing that I'd like to emphasize here is that while I will be showing a lot of results in robotics, these types of meta-learning algorithms are actually general to a wide range of applications. People have used it for program synthesis, for density estimation, federated learning, multi-agent learning, etc. I'd be happy to talk about some of those applications after the talk. Okay. So far I've talked about how we can learn to adapt a model with a very small amount of data through meta-learning. And I showed some examples of image recognition, reinforcement learning, and imitation. Now let's go back to the kind of chart that we had before. So meta-learning in these cases can handle raw sensory observations. It can handle a bit more diversity. But critically, what meta-learning gives you is it gives you the ability to acquire new skills with small amounts of data by learning how to learn across previous experience. What meta-learning doesn't give you is, while it can learn new things with small amounts of data, it still requires a lot of supervised experience on all of your previous tasks. In particular, what I mean there is for example, in the case of few-shot supervised learning, it can learn to discriminate between new classes with small amounts of data, but it requires tasks to be constructed from a fully labeled data set. And likewise, in the imitation learning setting, it requires demonstrations for many different previous tasks. And in the case of the ant here, it requires many tasks with the corresponding reward function. In providing these labeled data and reward functions for many different tasks is actually a significant burden. And it, in some ways, makes these meta-learning algorithms impractical for some applications. In essence, you can view meta-learning as moving the burden of designing learning algorithms to the burden of designing these task distributions. And once it has a task distribution, it figures out the learning algorithm and applies it to new settings. And so if we can remove the burden of designing the task distribution, then we can get a fully automated algorithm that can learn how to learn from unlabeled data and unlabeled experiences. So how might we go about doing that? First, let's consider the question, can we meta learn with just unlabeled image data? To do this, we'll need to construct tasks without labeled data. And essentially, we'll need to basically propose tasks from these unlabeled data, essentially propose different labelings for the data. If we can propose different labelings for the data, then we can potentially propose different tasks using those labelings and run meta learning with those tasks. So we'll discuss potentially one way to do this. So the approach that we tried here was to first run unsupervised learning to get some embedding space. If we ran unsupervised learning, we can then embed the images that we have into potentially a lower dimensional space. And then using this embedding space, we can propose tasks. What we're going to do here is we're going to propose tasks. We're just going to simply cluster this embedding in several different ways. So we might generate clusters with different clustering algorithms or different weightings of the embedding space to generate different potential labelings of the data. And then once we have these different clusters and these different labelings, what we can do is we can sample a set of clusters as the set of classes that will be that corresponding to a particular task, and then sample data points from those clusters, two of which will be used for, or some of which will be used for the training data, and some of which will be used for the test data, essentially. We can do this for, we can iteratively sample new clusters to generate new tasks for our meta learning algorithm. And then once we have these tasks, we can just run meta learning over these tasks in order to acquire a learning algorithm that can learn from data more efficiently than learning from scratch, per se. Okay, and then kind of the result of this is that we'll get a representation that's suitable for learning downstream tasks. In the case of mammal, you'll get an initial parameter vector that's suitable for fine-tuning to new tasks. Now the key question is, how does this representation compare to a representation that you get from kind of standard unsupervised learning techniques? And that's the question that we'll look at in our experiments. So for unsupervised learning, there's kind of a few different options that you can do here. We tried 4 different things. 2 of them were BiGAN, which is a generative modeling approach to unsupervised learning, as well as decluster, which applies discriminative clustering to image data. To propose tasks, we ran clustering, as I mentioned before, which we called Cactus, as a way to automatically construct tasks for unsupervised meta learning. And then we tried 2 different meta learning algorithms, mammal and prototypes. And so you can essentially, one of the most successful methods that we saw was the kind of the combination of Cactus and mammal, or a Cactus mammal. Okay, so let's look at mini ImageNet. So in mini ImageNet, we first can get some kind of upper bound on performance of using the fully labeled data, which is 62% in this case. And then we looked at running unsupervised learning. So we wanted to try actually a lot of different approaches towards using the unsupervised embeddings that we used. So one is just doing k-nearest neighbors on the embedding space that you have. Another is using logistic regression. Another is to use a neural network plus a lot of dropout to prevent overfitting. All these cases got around high 20s, low 30s. And finally, we also wanted to look at if the clustering was benefiting us. So we looked at the performing clusters and then matching those clusters to the test data points. And we saw slightly worse performance with that. Okay, and then if we instead use the BiGAN embedding cluster and then run meta learning on that, what we get at test time is actually significantly better than just using unsupervised learning, getting 51% on this data set. And this is 51% in terms of 5-way, 5-shot test tasks. And then we actually also do even better if we use the deep cluster embedding, where we're getting 53.9%. And I guess one of the surprising things is that this didn't just hold for mini ImageNet, it also held for 4 different embedding methods, 4 different data sets, so OmniGlot, Latent, mini ImageNet, and MNIST. 2 different meta learning methods with the kind of the caveat that prototypical networks was underperforming in some cases. And also test tasks with larger data sets. So it wasn't just 5-shot data sets, we also tested 50-shot data sets where you had more substantial amounts of data for the test costs to be So this is quite nice. This is, I think, basically you can achieve few-shot learning without requiring full labeled data sets previously. Now, what about unsupervised meta-reinforcement learning? Can we do the same thing, but with experiences that are in some environment? So we'll follow a general recipe that's somewhat similar to the recipe that I showed previously. In this case, we're assuming that we're giving some environment, and we're going to be trying to meta-learn in that environment. And then given that environment, we will alternate between trying to acquire tasks and running meta-learning on those tasks. And then after meta-learning, we'll have an environment-specific reinforcement learning algorithm that can be then used to take the reward functions and provide a policy that maximizes that reward function. In particular, it can maximize that reward function more efficiently than reinforcement learning from scratch. Okay. So kind of the key part here is actually how do you acquire the unsupervised tasks. So everything else is generally are things that we already know how to do. So we tried two different things. The first is quite simple. Is a bit I guess somewhat like the other one. It's just to randomly propose tasks. What we can do is we can just randomly initialize a neural network to kind of initialize a discriminator on these states. So it's going to act on a given state and produce the probability of a state. Where in this case, D will be a randomly initialized neural network. And essentially what this amounts to is partitioning the space into different regions, and these discriminators are going to operate and give some probability on these regions of the state space. This is actually a quite simple thing to do, but actually in some cases it does surprisingly well. And what's really important here is that the reward functions are over state space, not over policies. For example, if you consider a Markov chain, if you're trying to search over random policies, you're going to have an exponential search to find the correct policy, whereas if you're searching, if you have random reward functions and you're searching over the space of reward functions, then you have a polynomial search problem to try to reach your goal state. Okay. We can actually do slightly better than random search, so or random reward functions, and I'll discuss those here. So this is actually going to look quite similar to the clustering that I showed previously, and that it's going to try to actually propose tasks that are more diverse from each other, rather than simply proposing random tasks. And the way this works is this is building upon previous work by Ben Eisenbach, Abhishek Gupta, Julia Ebers, and Sergey Levin. And what it does is it tries to have an agent interacting in an environment and is trying to learn skills that are discriminable from each other. And the way that it does this is it has a policy that tries to visit, is rewarded for visiting states which are discriminable, and a discriminator that is trying to predict the skill from the state. So this ends up being a two-player cooperative game where one player is trying to discriminate between the different skills based on the states that the policy represented, and the other player is trying to visit states that are better discriminable, makes the job easier for this discriminator. Okay, and the reward becomes the log probability. Okay, so here's some examples of the types of tasks this algorithm learns, and these are the tasks that we're going to be using for unsupervised meta learning. Okay, so if we look at the results, these are all showing test tasks that were not seen during the meta learning process and only seen after the unsupervised meta learning phase. And these are showing learning curves. So the x-axis is learning iterations at test time, and the y-axis is reward, where blue is random, red is just learning from scratch, blue is random goals, and green is showing the diversity-driven goals. What we see in all cases is that the diversity-driven goals is doing significantly better than learning from scratch. And in some cases, using just random goals and random reward functions actually does surprisingly well and outperforms learning from scratch. Okay, so for me, the takeaway from both of these two works is that we can actually get good performance from meta learning algorithms with relatively simple mechanisms for proposing tasks. And I also expect that if we're able to develop more, more complex yet more sophisticated approaches for proposing tasks, then we'll actually get even better performance from these types of meta learning algorithms. Okay. Finally, I want to talk about if we can do this online in the real world. And so if we want to be able to perform meta learning on a real robot in the real world, we need two things. We need sample efficiency, because it's expensive to collect data in the real world. and we need some distribution over tasks. And we don't really want to design this distribution over tasks manually. We want the robot to be able to figure it out on its own. So first, let's talk about efficiency. So for efficiency, we're going to use a model-based approach to reinforcement learning because these algorithms are typically much more sample efficient than model-free variants. The way is kind of the model-based RL approach that we're going to build upon simply goes from collecting data, fitting a model to that data, plan using that model, using model predictive control, and then repeating that process. So planning using that data and taking rollouts, and then adding that to our data set to refit our model and improve our model to that data. Okay, so one thing that you already get with this type of approach to model-based reinforcement learning is you already actually get zero-shot adaptation to do reward functions. Once you have a model of the environment and you're trying to plan using that model, if you're given a new reward function, you can just plan with respect to that reward function. So in this case, different tasks are actually going to correspond to new environments, or different aspects, or different terrains of the environment, or different dynamics, essentially. And essentially what this amounts to is online system identification. So we want to be able to figure out the dynamics model at any given point in time. Okay, and this is work done by Anusha, Ignacy, and Samin. And let's kind of look at an example here. So say we have this robot that's taking some path, and at different points in the environment, there's different conditions and different things that are changing, like a gradual terrain change, or motor malfunction, etc. If we kind of can flatten this out, our goal is going to be, given a very small slice of time, adapt our model of the environment, and then plan with respect to that model. And kind of one thing you can note here is the problem of this like online adaptation problem is exactly the same as, or it's an instance of the few-shot learning problem. Because we want to be able to, given k time steps, be able to adapt our model to the next time step to be able to effectively model that aspect or that time slice of the environment. The second thing that online adaptation corresponds to an instance of the few-shot learning problem where tasks are temporal slices of experience. The other thing to point out is that in this case, the task distribution is more or less free. If you have a diverse environment, visiting different parts of that state space and different aspects of that environment corresponds to your tasks. So the environment is just giving you your tasks. Okay. And so what kind of the online adaptation process will look like is we'll have our recent history, we'll adapt our model to that recent history, and then take an action by planning, and then repeat this process. And critically, kind of where meta-learning comes in here is when we're doing this online adaptation, we're going to use a meta-learned prior that's going to enable us to effectively adapt with very small amounts of experience. For meta-learning, we tried both an RNN-based approach as well as a mammal-based approach. Okay, so let's look at some of the results. We first looked at some simulated domains. In this case, the top setting is that one of the legs of the ant becomes crippled in the middle of the rollout. And in the bottom case, each of these platforms have different damping factors, essentially like a pier, and the robot needs to adapt to the different damping factors. And it can do that when it has this meta-learned prior and is faced with this dynamic environment. And the really important thing about these results is the efficiency. So we compared this to two model-free approaches, and we see that our algorithm is significantly more sample efficient and can learn with an amount of data that's feasible to run on a real system. So then we took it on a real system. We looked at this roach robot. This is basically a handmade robot. The dynamics are incredibly complex as it's running dynamically across different terrains. We meta-learned it across, I think, 4 or 5 different terrains. And we tested it on different situations, including different slopes, a missing leg, so we removed one of the legs from the robot and had to adapt to that online, a different payload, and errors in the mocap calibration of the calibration of the pose estimation via mocap. And across all of these different settings, we found that our method, kind of using meta-learning, which is shown in green, was able to significantly outperform 2 alternatives. So the darker pink is showing just a model-based RL approach that's trained on all of the data that isn't trained to specifically adapt to different data. And the light green is model-based plus dynamic evaluation. So it's something that's trained to model all of the environments, and then it runs gradient descent to adapt online to the different environments. But it's not actually trained to effectively adapt. It's just running gradient descent at test time. And so as a result, it isn't able to effectively adapt with very small amounts of data. Okay. So here's some examples of what it looks like. So this is a slope. It's a bit hard to see that it's actually a slope in these videos, but you can see the slope on the bottom left. And the goal here is to run in a straight line path. What we see is that ours is able to effectively run in a straight line path, whereas the model that isn't actually trained to adapt falls off course because it isn't used to being on the slope environment. And here's another example where the goal is to run in a straight line path. In this case, one of the legs was attached to the front right leg. And so these robots have a tendency to need to go right. But by adapting online, our method is able to maintain a straight line path, whereas just using model-based reinforcement learning without any adaptation can't effectively recover. Okay. Now, one last thing that we've been experimenting recently is considering the case where we have different changes in our environment, but we also have some new terrain that's very different from anything that we've seen previously. And this is really, I guess, this is something that we can't handle previously is because only a very small snapshot of experience won't be enough to adapt to that new terrain. And this is also really important because in the real world, an agent is going to be faced with tasks that it's never seen before, with terrains that it's never seen before, and it needs to be able to learn online and accumulate experience to effectively solve that task and to effectively adapt to that terrain. So K-shot isn't enough, and one thing you might ask is, well, you could just continue running gradient descent. This will perform well if you are perpetually on that new task or on that new terrain. But then once you switch to a new terrain or kind of conditions change or you're given a new task, continue to run gradient descent, you'll just overfit that terrain, and then when you see new things, you won't be able to effectively kind of switch back to what you did previously or be able to learn for that new setting. Okay, so how might we go about doing this? Essentially, to solve this problem, what we want to be able to do is, at any given time step, we want to be able to identify what condition of the world that we're in or what task we're trying to solve. This is something that isn't necessarily given to us. In the case of terrain, we don't necessarily told that we're in a drastically new condition. So we need to infer this information. So we pose this as an online inference problem where we want to be able to infer some latent information about the state. We're going to call this a latent task variable in the meta-learning sense where we might be meta-learning over different tasks. We want to be able to infer this latent variable at every single time step. And then once we have this task variable, we maintain a mixture of neural networks over this task variable, which is going to be adapted continually. So we're using this notation as kind of a different parameter vector for each task. And then we can kind of perform this inference problem with an EM-like procedure. So we're going to be alternating between ESEP, which estimates the latent variable at each time step given the data. This just looks like the product of the kind of likelihood of the data under that task times some prior. In this case, we use a Chinese restaurant process prior. And the M-step, which is going to be updating the mixture of neural network parameters online after performing this inference. And what this just amounts to is gradient descent that's weighted by your probability of the latent task variable. Okay. And one thing to note here is this form of online learning, in general, won't work if you're starting with a random initialization for a neural network, or a neural network that's just trained with standard supervised learning. What's really important here is that we initialize this online learning process with initialization that's learned with mammal. And as a result, we get something that can adapt very quickly from small amounts of data or modest amounts of data rather than being trained rather than being in some part of the parameter space that isn't effective for this type of adaptation or online learning. Okay. So we haven't looked at real-world domains yet, because this is very recent work. We looked at this crawler robot, and we compared to kind of a constant crippling setting where it's only a single task at test time versus a task that's alternating between normal regions where the robot is not crippled and where the robot is crippled. Essentially, this is evaluating its ability to infer the latent task variable in these different regions and being able to then effectively adapt to that setting. And then we plot normalized ROR on the y-axis. And we looked at a number of different alternatives. Ours is going to be shown in green. Red and blue is two different types of meta-learning methods that don't use this online EM procedure. And black and light blue are going to be showing model-based approaches that don't involve any meta-learning. What we see is in the constant setting, all of them perform roughly around the same, which is roughly what we would expect. Whereas in settings where we have regions of kind of both normal and crippled legs, we see that our approach is able to outperform the others by using this EM procedure. It outperforms meta learning methods, and by using meta learning, it's able to outperform the model-based methods. Okay. And then we can also look at the latent task distribution over time and see that it can actually effectively infer these task variables over these different regions of time. Okay. Then kind of the next step here is to run it on the real robot. We haven't done that yet. Okay, so to wrap up kind of the takeaways of what I talked about today, first I showed how we can learn sensory motor skills from scratch on a real robot, how we can use meta learning to learn new concepts from small amounts of data, how we can meta learn representations without supervision, and how we can adapt online in the real world. Now I'd like to discuss kind of what's next and where we go from here. So kind of my general goal, my long horizon goal, is to be able to build generalist learning systems that can operate and learn not only in simulation and lab environments, but in the real world too. And I think this is really important because the real world exhibits such diversity and such complexity, and I think that that complexity will will challenge the algorithms that we have, but also with greater diversity requires, greater, more interesting behavior and higher levels of intelligence to be able to handle that diversity. Even though this is quite a long-term goal, I think that there are kind of missing pieces that we can work on to make progress. The first is the ability to learn without human supervision, as I've talked a lot about today, but also explore and do this from raw pixel observations. We actually have a fair bit of work in this direction of a robot being able to try to learn from learn different tasks like pushing objects and arranging objects and manipulating deformable objects just from raw experience. But there's still, I think, a lot of important work that needs to be done in this direction, especially in the realm of exploration, and being able to actually direct exploration towards the types of tasks and towards the types of behaviors that are more interesting and more challenging. Second, I think, is the ability to convey and understand complex goals. So I guess things like being gentle or cooking dinner or trying to console someone. These things are incredibly complex for a machine to understand. But for a machine to be able to understand them, that's kind of the prerequisite for the machine being able to perform them. I think that things like kind of learning from videos of humans and learning gold classifiers are potentially some first steps in this direction, but ultimately we need systems that can learn from things like language, from audio, from body language, and be able to kind of use all of those signals and prior knowledge to understand such complex goals. And then finally, is the notion of continual learning. So meta learning is essentially can be viewed as one step of adaptation, taking experience with many other objects to quickly adapt to new objects. But ultimately, we want systems that can then take experience with new objects and continue to learn towards more complex and more interesting and more diverse situations, kind of continually performing meta learning in order to effectively build upon previous experience and build greater and greater levels of intelligence over time. And then kind of ultimately combining elements of continual learning and self-supervision in order to learn in the real world in unstructured environments. Okay, with that, I'd like to thank all of my collaborators, many of which made many contributions to the work that I presented today. And a lot of the data and code for the papers that I mentioned is linked on my website, and I'd be happy to take more questions. Thank you.